if you want to represent absolute error, in function, and the function is y equal to f of x. So what will you get? So we know that change in y is equal to change in x, that is error in x, multiplied by derivative of f of x. This is the quantity. So if I want to compute absolute error, we know that absolute means we need to find the absolute of this quantity. This, and this. Okay. So but absolute error is represented by this. So what we have now, absolute of this quantity is equal to this quantity. So what we have, we can say this quantity is further represented as this amount. So now this is the same similar quantities, epsilon y. If this, then this is equal to this. But keep in mind that there is an identity which says that this amount of error cannot be greater than, this amount is less than and equal to epsilon of x modulus multiplied by epsilon of f dash of x. I hope you all remember this idea. So what I did, I shift this absolute sign to this quantity. So if error is defined, then absolute error ends here. This is the error. But this is the interesting relation. It says that the absolute error amount cannot be go greater than this amount. This is the absolute quantity of epsilon x, that is error in x, multiplied by absolute value of this individual value. So multiply them, whatever be the answer you get is not going to greater than this part. Just for a food for thought, what does this mean? For example, this is the rough work or extra part, let's say. So for example, I have a number 2 multiplied by 3. So if I take the absolute value of this quantity, so this is equal to, this could be written as 2 into 3. So what we have here, we have 2 into 3 is exactly equal to 6 absolute equal to 2 into 3. So absolute of 6 is 6 equal to 6. They are equal. Now what happened if this thing 2 into minus 3? Okay, so in this case this is equal to 2 absolute minus 3. So if you multiply these two, you will get minus 6. You need to compute this absolute, and this equal to 2, I mean only 2 multiplied by 3. So this is equal to 6 and this is also equal to 6. So in this case they are equal, both are equal. So in fact I have a mistake here. These two quantities are equal. Let me clarify this part. This is these two are equal all the time. These two are equal. So what I can say, because I mix it, in case of addition we have this relation, but in case of multiplication, the absolute error is the absolute value product of the individual quantities. So this is kindly correct this statement, that the absolute error in a function y equal to f of x is similar to this quantity. They are equal. So what you have to do, I have to just, if I ask you to represent your error of a function in the form of absolute error, which means that these two quantities, you just need to take the individual absolute error and multiply them. So you will get the answer. So this is the absolute value. But similarly, if someone asks you to represent in a percentage form, so it is quite simple. You can represent it percentage form or a relative error, but I am using the percentage error. How we can do that? We know that we need to divide absolute error by certain reference. So here the reference is the correct reading. Correct reading is y. So if you divide this quantity and multiply it by 100, you will get the percentage error. So is this means that in the form of functions we can similar do the all the calculation because we have this representation in general. So if you have an error, you can represent it in the form of percentage error or a function error or any other type of error. I hope you understand the idea. So kindly clarify this thing, remove this part. It is equal. So this part is equal to that part in case of multiplication. I remember now. Okay. But before to going to example problems, let's think about another possibility. In fact, I have already given you this example. What is the error in function in the case where function depends more than one variable. More than one variables. This is interesting. So student, I have given you an example of y equal to f of x. So we know that this is one variable and this is one variable, and this function y variable y is depending on x only through the function f. So this is very simple example we have discussed. But my question is, what will happen? For example, you have a function y equal to f, but it's depending on x, is depending on p, is depending on t, is depending on q, and there are many other variables. So question is, what will we do? Because in this case we have a similar issue, but in a more complicated representation, because this y can be changed or influenced not only by the x, not only by the p, not only by the t, not only by the q. However, this could be changed or get error based on all these variables at a time. For example, the correct reading of x is x, but I made a mistake and note down x dash. Similarly, the correct reading for the function is p, but I made a mistake and noted p dash. Similarly, t dash, q dash. So what will happen if I replace all these readings in that function? Obviously, they will impact y. So this means that if the function is depending more than one variable, it will create error if we note down the variables wrong, but the impact on the variable is simultaneous. It will represent the error in a combined form. It will be show the error, that is the total error in the function. So how do we compute the error in this case? So rather than using x, p, t and q, let's make it easier for you. So consider a function y which is depending on the following variables: x1, x2, x3, x4, and let's say there is some variable xn. So how many variables are there? N variables. For example, if n is 5, I will say my function is depending on 5 variables. Here it is depending on any n variables. Similarly, if I made mistake in any of these variables or all of them, I will get some impact on y as well. So let's say the change in y is also influenced by this variable. So what I have to do, I have to find the change. So the change in this case is defined as, I'm giving you direct relation, the change in y is equal to, what you have to do, student, you have to know the change in individual variable. So the change in x1 is epsilon x1, which you know. Okay, that amount of error I have made in x1 only, multiply by, this is the interesting thing, and I hope that you all remember this part. This is the change in x1 of f function. But keep in mind, this is not ordinary derivative, this is the partial derivative. What I have to do, I have to compute the partial derivative of this function with respect to the variable x1, plus, this is the different part, plus epsilon x2 dava f divided partial derivative with respect to x2. Similarly, epsilon x3 dava f over x3, and so on till the last variable epsilon xn, so epsilon xn dava f upon dava xn. Now this is interesting. Let's see. Let's say this is only a function depending on a single variable. So this means there is only x1. In this case, there is no influence of other variables. So in that part, there is no error in other variables. So this means epsilon x2 goes to 0, x3 goes to 0, and so on. So this whole term will be 0 in this case. So only left is epsilon y is equal to epsilon x1, this thing. So this is exactly the same formula for a single variable if I consider the function for a single variable. But here the function is depending in more than one variable. So this is the formula that I have to use. The only difference is now I have to compute something called partial derivatives, not ordinary derivatives anymore. And I hope you all know how to compute that. Also, we will recall the example as well. So the main, usually in engineering problems, we have to deal with this type of function. Although single function is also acceptable, but usually we have to deal with these type of functions. Let's call it 2. Because usually the engineering problems are complicated, so we have functions that are depending on more than one variable. What does the example that can be used here? So example that I can use here is same example. For example, uh, same example, I mean, with same I mean to say the Ohm's law example that I gave you earlier. Ohm's law, it says voltage is defined as the product of current passing through it certain and the resistance. So let's say we have an experimental setup in which we can vary both of these variables, the current and the resistance, which we all know that we can do this by varying current and resistance. The voltage will get some impact. Let's say the instrument that we are using has some problem, and due to which instead of getting I as the exact reading, I got I bar plus epsilon of I. Similarly, instead of getting correct resistance reading R, I got R dash plus epsilon of R. So in our calculation, we are not going to use I and R. We will use I. This is I students, I bar, I dash, and R dash. So one can clearly see if I plug I dash into R dash, so this is not going to be V, it should be a V dash because it contains error because I am not using the correct reading. So now the question is, what amount of error that we have introduced based on these two amount of mistakes in current and in resistance respectively. So I can clearly relate this problem with the example that I have shown you in the last slide. That is a function of more than one variable. How I can relate them? Very simple idea. I can say the voltage here is a function of what? Current and resistance. I can represent Ohm's law like that. And what is the value? What is the actual representation of the function is equal to I times of R. We can do that. We want to say voltage is dependent on function, which is defined like that, and the function is depending on I and R. So what this I and R has to do with our last example, this I can be regarded as x1 and this R can be regarded as x2. So this function is an example of two variable function. The voltage is depending on two variables in certain example. So if I want to ask what if I made these two mistakes, I know these mistakes, then what change will it will bring to my delta V, I mean the voltage reading. So I can write down like that. Epsilon V, that is the error in V, is equal to epsilon of I partial derivative of F with respect to I plus epsilon of R, that is resistance error, partial derivative of F with respect to R. Now student, we all know that epsilon of I is a given quantity or the quantity in a numeric. We know that okay, this is the amount, we will keep it like that. Now the main point is this quantity dawa f of dawa I. We know that this is the function, but the function is represented here and I need to compute this partial derivative. So how I can do that is a very simple concept. Dawa I R upon dawa I. So I need to compute the partial derivative. Similarly, epsilon of R dawa I R divided by R. So if I want to compute the partial derivative, I have to follow exactly the same rule of differentiation. The only difference is whatever be the variable with respect to we are computing a derivative, we will treat it as a variable and all other variables will be treated as a constant for the time being. Although they are not constant in general, but for derivative we will consider that there is no impact. So here I want to compute the derivative with respect to I. So I will consider this I as a variable and this R as a constant. I will take them out. If you like here, uh, we can take a break and if you like, because 40 minutes are roughly, so you can take a break as well.